Okay, in this video lecture, we're going to combine a little bit of algebra with logarithmic equations. Specifically, we want to solve given logarithmic equations for a specified variable. Solve for an unknown. Okay, let's talk about what we know. And we've got a fair number of things under our belt at this point. We know what a log function is, any function of the form y equals the log of b to the x, where the base is greater than 0 and not equal to 1, and the argument is positive. And we know that this log function outputs an exponent, so the log base b of x equals y is an exponent. We know that the exponential function y equals b to the x can be rewritten as a log function x equals the log base b of y. Again, this log function outputs an exponent, which is in this exponential equation is right here. And we know some properties of logarithms. The log base b of 1 is 0. The log base b of b is 1. The log base b of b to the x is x. The product property, the log base b of a product, equals the sum of the logs of the factors. The quotient property, the log base b of a quotient, is equal to the difference of the log of the numerator minus the log of the denominator. And I guess you might call it the exponent property. The log base b of x to the n is equal to n times the log base b of x. To do a little work with solving equations for a specified variable, we want to introduce I guess I'll call them two more properties. They're not really properties, so I'll put it in quotation marks. But two more things to be aware of, and they're the same take. It's basically two takes on the same idea. So, if m equals n, if a variable equals a variable, if these two things on the same side of the equal sign are the same, then we can take the log with the same base of both sides, and those will be equal as well. So if m equals n, then the log base b of m is equal to the log base b of n. Basically, you can take the log of both sides. Now that one's not going to be is not going to come into play today, but its reverse, which I have listed here as property 8, is going to come into play today. If you have the log base b of m on one side and the log base b of n on the other side of an equal sign, well, then you can, what I call untake the log of both sides, and that means the two arguments are equal. If the log base b of argument 1 equals the log base b of argument 2, well, then argument 1 must equal argument 2. Okay? So we're going to work with those. Now, how do we do this? I just jotted down a brief, I guess what the goal is, what we're doing here, kind of a brief couple of sentences. You know, the goal, let me make sure I got have my top part up here. I want to see that. So the goal is to work with these log equations. If we can get the goal becomes to get a single log on one side. If we can get a single log on one side, then we can go up to here. I have a single log on one side, and I can rewrite it in its exponential form. Okay, so it can be changed to its exponential form and solved. The second thing we'll take a look at here is if we work with log equations, we want to get a single log on both sides. Perhaps you can't get a single log on one side. Can you get a single log on both sides of the equations? If that's the case, then we can go to here, property 8. And we can say, okay, I got one log equals one log, same base. I can untake the logs and say that m equals n. and it can then do that and then be solved. So we're going to be looking primarily at up here and this one in this video lecture, and I'll do an example of both. Okay, turn my paper over, and let's take a look at myself. I hopefully straightened out. All right, we want to solve each of the following equations for y in terms of x. So we're going to solve for y. Okay, well, in example 1, the log base b of y equals the log base b of 6 minus the log base b of x. Well, the y is inside this log here, and I can't just divide. There's no such thing as dividing by a log. I mean, it's not being multiplied. It's within the function. So let's see. I know I can combine the right side, because it's a difference of logs, into a quotient, and that will leave me with a log on both sides. Okay, so the log base b of y is equal to the log base b of 6 divided by x. So there's our quotient property. If I have the difference of two logs with the same base, that's the same as the log of the quotient of the arguments. Well, now I have a log base b. I have one log base b on the left and one log base b on the right. So I can essentially say, okay, I can untake. If the log base b of argument 1 equals the log base b of argument 2, then argument 1 equals argument 2. So y is equal to 6 over x. And I just solved this equation for y in terms of x. If you want, you may see sometimes this is the same as 6 times x to the negative 1 if you want to have it written, not written as a fraction. So there's an example there of, just getting the right side, just combining the right side or working with the right side and your log properties to come up with a single log. I have a single log on the left, a single log on the right, which means their arguments are equivalent. I can drop the logs and I'm left with this. And in this case, it turned out to be I'm all done. Y equals 6 over x. Okay, my second example, we'll take a look at making use of that exponential function. Left myself a lot of space, apparently. Pi times the log base 4 of x plus log base 4 of y equals 1. Again, I want to solve this for y. Now notice, if I move this log over to here, I'm kind of stuck. I'll have a log on the left, but I'll have 1 minus the log on the right, and that's got too much going on. But I can combine these two logs. However, I got to deal with this first. I got to deal with that pi. Okay, I can't pi log base 4 of x plus log base 4 of y. I can't do that. But if I take advantage of property 6 and I move the pi over to here, I'll have log base 4 of x to the pi plus log base 4 of y. Okay, now I have the sum of two logs. And I know that the sum of two logs is equal to the log of the product. So this is the same as the log base 4 of x to the pi power times y, equals 1. So I've got myself now where I have a single log on one side of the equation and a non-log on the other side. So I can rewrite this, and I like to use my arrows, as an exponential function. 4 to the first power is equal to the argument. Base to exponent equals argument, which is equal to x to the pi times y. That's pretty cool. I'm going to rewrite it with the x pi. 4 to the first power, of course, is 4. So this is x to the pi times y equals 4. And now I can solve for y. I'll divide both sides by x to the pi. Of course, x to the pi divided by x to the pi is 1. And so I'm left with y is equal to 4 divided by x to the pi. And again, if you want to write it as not a fraction, then that's equal to 4 times x to the negative pi using our properties of exponents. Again, I'm fine here, but sometimes they may want to say, I don't want it as a fraction form. I want it to be as a kind of a single term, if you will. So there you have it. Okay, a couple of examples. What we're after here is, can you get a single log on either side? Because that allows you to remove the logs and work with it. Or can you get a single log on one side and a non-log on the other side? Because that allows you to take advantage of the exponential form, which you can then work with.